Dissociation is important when looking at the products of combustion. My name is Condra and I'm Associate Professor at the Department of Energy Technology, Aalborg University, Denmark. And I'm going to show you how to determine the products of combustion taking dissociation into account. What we're going to look at is the concept of dissociation. We're going to look at dissociation in combustion. So, if we take a very simple reaction of methane plus atmospheric air, when it combusts, we will form CO2 plus water plus N2. So if we balance this reaction here, we'll find that the coefficient here is 2, the coefficient here is 1, this one is 2, and this is 7.52. Good. Now if we make some measurements of the products, I should perhaps simply say that the products will have a temperature, typically a temperature of about 2300 Kelvin. That's approximately the adiabatic flame temperature. Now if we look at the products, we can see CO2, H2O, but if we actually make some measurements, we will actually find that we will find some CO2, we will find actually some CO, we will find water, we will find O2, we will find H2, we will find OH, we will find N2, NO, etc., etc., etc. We will find many other components. Now, this so-called splitting of molecules, what happens here is that the molecule of CO2 actually splits into a CO and actually an O2. So it splits into two molecules. Similarly, water will actually split into H2, some O2, maybe some OH, etc. So this splitting of molecules, this is what we call dissociation. Now, dissociation actually will occur at room temperature. So in this room here, there is O2, there's actually also O and O3, ozone. There's also water, a small amount of water in the air. There's actually also H2, which comes from atmospheric air. There's also H and everything else. But the dissociation which occurs at room temperature is extremely small. So dissociation is normally associated with high temperature. Now, normally you say that the high temperature we're talking about here would be in the region of, say, greater than 1500 K. This is when dissociation begins to become significant. If we raise the temperature up to, say, something like 5000 K or above that, then we get what is known as a plasma. And a plasma simply means that the molecules would actually split up. You will get all of these components plus actually free electrons and ions as well. But this is very high, very high temperatures. So what we're going to have a look at now is how do we determine how much CO2, how much CO, and all the other components are there in the products of combustion. Now we're not going to take this reaction here with CH4, but I'll take something which is a little bit simpler. So, how do we determine that? we determined that this comes from the second law of thermodynamics, and this is also associated with what we call the Gibbs function. Now the Gibbs function, I just simply tabulated values for different components. I'm not going to go into those details about that. We'll just simply concentrate on trying to determine the components for the moment. So what happens at this 2300 is that the first molecule, if you like, to put it simply, the first molecule that actually splits is CO2. Now CO2 will actually split into CO2 into CO plus 1/2O2. Now if you notice here that I have an arrow going forward and an arrow going backwards. There is no international convention on exactly how you write this, but the idea with this one here is that the reaction actually is going forward like this. So CO2 is splitting into CO and O2. It's actually at the same time it's going backwards. So CO is combining with O2 to give you CO2. And the thing about this is occurring on what we're going to look at is occurring under equilibrium. And equilibrium simply means that the rate of reaction going forward is the same as the rate of reaction going backwards. So if we make a very simple graph of what's occurring over time, of say some sort of component. So we have some sort of a component here, which could be CO2. If we look at what's happening is that the CO2 will be formed. We start up at 0. Over time. Now the time that this occurs is very short. It's much less than 1 second. So if we look at this graph here, we can see that we start off with the reactions occurring actually backwards and forwards as well at different rates, and this is sometimes known as the kinetics part. This part here, from this point onwards to, you could say, to infinity, that is the equilibrium. Equilibrium is much easier to study than kinetics. So what we're going to look at it now is what's occurring out here. And what's occurring here, as I say, is that the reaction is going forward and backwards at the same rate. Now, the reaction that I wrote before was CO2. This one goes forwards and backwards to CO plus 1/2O2. Another reaction would be H2O going forward and backwards to H2 plus 1/2O2. So how many reactions are occurring in this combustion under equilibrium? There are literally hundreds of them occurring, but the main one, the one that occurs first and gives the biggest, most significant difference, is this reaction here. So what I'm going to do is I'm going to take a very simple example. I'm going to take carbon monoxide, which can be a fuel that's used, say, in refineries, which is a product. And when I combine this with air, atmospheric air, O2, plus 3.76 times N2, we will combust this, and you will get CO2 plus N2. Now if we do the balancing up, we'll find out that this one becomes, coefficient here becomes a half, this one becomes 1, and this one becomes 1.88 here. Now the N2 is going directly, half of this one over here, directly over to N2 over here. Good. So now when we consider that this composition here, which occurs here, we assume that this composition here is at 3000 Kelvin and is also at 1 atmosphere. Now this is not necessarily the combustion temperature of this. We would have to preheat this to a very high temperature to get 3000 Kelvin. But at 3000 Kelvin we're going to get significant dissociation. So the big trick here is to look at this products of combustion in a way as reactants. So we know that CO2 is going to split. The N2 will not split, so the CO2 will split. So what we do is we simply write 1 times CO2 plus 1.88 times N2. And you notice that this one is going forward to N1 times CO2 plus N2 times CO plus N3 times O2 plus N4 times N2. So what we do now is we do a carbon balance. And this simply means we balance the number of carbons which are on the right hand side to the number of carbons which are on the left hand side. So we start off with 1 carbon here, so that becomes N1 plus N2, and that's equal to the number of carbons on the left hand side, which is equal to 1. Now for convenience, what we will do is we will rewrite this one as N2 is equal to 1 minus N1. Now what we do is we do an oxygen balance. Now the oxygen balance simply says we have 2 times N1 plus 1 times N2 plus 2 times N3, and that is equal to the number of oxygens we have on the left hand side, and that's just simply equal to 2. Okay, so if we take now our N2 and plug it in there, and we have 2 times N1, if we do this, then we'll find out that N3 is equal to 0.5 times 1 minus N1. Good. So now we do the nitrogen balance. And this is very simple because we have 2 times N4 is equal to 2 times 1.88. So that was easy because N4 is equal to 1.88. And we could have seen that from the beginning. Good. So what we're going to have a look at is what is the composition under what we call equilibrium. So this is the composition we're trying to determine. What are the coefficients here? What are the numbers? So in order to do that, we make the use of the equilibrium constant. This is often given the sign as Kp. The Kp, this refers to the reaction which is given up here. The Kp value for this reaction under 3000, okay, Kp is equal to Kp is equal to 0.31. And this is actually just only a function of temperature. Now, Kp, the expression for Kp, that one, these are ideal gases, so the expression is equal to P over P0 raised to a coefficient of 1 multiplied by P over P0 raised to a coefficient of 1 over 2 divided by P over P0 raised to a coefficient of 1. Now what does this refer to? This refers to CO, this refers to O2, and this refers to CO2. Now I'm not going to show the derivation of Kp, but in simple terms, with Kp you always have the, what I would say is the reactants on the underneath the line and the products above the line raised to the stoichiometric coefficients. And the stoichiometric coefficient here is 1, this is 1, and this is a half. So this is the reason why we have a half up there. Now, P0, that is a definition. This is the standard pressure. This is equal to 1 atmosphere. And also we have, if you like, our P reaction is equal to PR, and this in our case here is equal to also, we give it a sign of PR is equal to 1 atmosphere as well. Good. So, what does P over P0 say of CO? What does that mean? The P0, that was equal to 1 atmosphere. This one here is equal to the partial pressure of CO. And the partial pressure of CO is equal to P reaction multiplied by the number of moles of CO divided by the total number of moles which are in the total number of moles in the composition that we have. Similarly, PO2, that again is equal to P reaction, the number of moles of O2 divided by the number of moles, the total number of moles given here. So we're going to need this total number of moles. So the total number of moles, that's simply the sum of all the moles that are in, of all the moles of the components, and that's equal to N1 plus N2 plus N3 plus N4. Now if we plug in, we know what N1, N2, we know that N2 and N3 as a function of N1. We know what N4 is already. So if we plug those in, we get 0.5 times 1 minus N1 plus 2.88. So if you like, we instead of having 4 unknowns, actually we only really have only one unknown. Well, this one wasn't really unknown anyway because the nitrogen doesn't react. So we plug in these expressions into our Kp value. That becomes equal to N2 divided by N total raised to 1, N3 divided by N total raised to 1 over 2, and N1 or N total raised to power of 1. And the pressures will appear out here. This would be P reaction divided by P0. Now P reaction is equal to 1 atmosphere. This is equal to 1 atmosphere. So this term becomes equal to 1. Good. So we know what N2 is in terms of N1, similarly for N3. So if we plug all this in together, we'll get, after a little bit of work, you will find out that this one is equal to 1 minus N1 divided by N1, 1 minus N1, 1 divided by 6.78 minus N1 raised to 0.5. Now Kp, as we know, that should be equal to 0.31. Now this is just simply a nonlinear equation. It can be solved in a number of ways. Simplest way is actually using fixed point. If you solve this one here, you will find out that N1 is equal to 0.484. So this simply means that the total composition is equal to 0.484 by CO2 plus 0.526 of CO. Remember that N2 was simply equal to 1 minus N1 plus 0.258 by O2 plus 1.88 times N2. And just as a matter of interest, we total all the moles up, we find out N total is equal to 3.14 kilomoles. And if we take the number that we had without dissociation, that was equal to CO2 plus 1.88 times N2, and that was equal to 2.88 kilomoles. So we can see that actually the number of kilomoles actually increases. So, and this also means that in actual fact the molecular mass of the gas products is actually increased when we take dissociation into account. I hope you've learned something from this short presentation. If you want to look at some other education examples, just have a look at my YouTube channel. Thank you.